Welcome back. Let's talk about languages and grammars. Here's the agenda. We'll start off with basic definitions. Then we'll compare what we know with natural languages like English with formal grammars. We'll look at some different kinds of formal grammars. And then lastly, and most importantly, we'll look at formal grammar examples. This is the meat of the thing, is the formal grammar examples. But we really do need to go through all of this theory in some detail before you can really understand what's happening with these examples. All right, so let's get started. We'll start off with some basic definitions. Our first definition is an alphabet. Okay, an alphabet is a finite set of atomic symbols. By atomic, we mean indivisible. That is, it cannot be broken up. Now, what we mean by indivisible depends on the alphabet, really. So here's an example. Let's use the actual alphabet. We'll just use the lowercase letters to keep it simple, but the actual alphabet is a finite set, right? And you can't really break up a little a into anything. It doesn't really make sense. You can't have piece of a little c. So these are indivisible, okay? Here's another alphabet. So we use the capital letter B to indicate an alphabet, and it consists of the elements 0 and 1, right? And you could build strings by concatenating, by just concatenating all of these symbols together. We'll do that in a minute. Here's another alphabet. Okay, these are all clearly indivisible, right? It's hard to imagine breaking these up. But here's another alphabet. Now we're calling this an alphabet, although these are words, but they're indivisible, right? In English, words are indivisible, typically. You don't really break up cats into something smaller than that. Now, most of the time we're going to be doing math, so we're going to be using just these single symbols, but keep in mind that these single symbols could be used as placeholders for these larger elements here. Now, we'll do that at the end when we look at a natural language generator implementation. Okay, so try and keep this straight. It's a little bit easy to get confused. But anyway, just to reiterate, what we mean by indivisible depends on the language. So words are indivisible in this particular language, and these words. What we use the word words to talk about English. Here, we're mathematically we're talking about these as an alphabet because it's a set of indivisible symbols. So that's an alphabet, mathematically speaking. Okay? The next thing is a string. A string is a sequence of atomic symbols. You can take any one of these alphabets and start stringing the symbols together to get strings. So, for example, you could take the first alphabet here and you could generate any number of possible strings. A lot of them would be noise, but this one isn't, right? According to what we consider, to be English, that's a valid string over this set A. So we use the terminology a string over A. And this is one example string that you could generate. Using set B, you could generate a string that looks like this. We would call that a string over B. Using AB, we could generate a string called, the string ABA, and we call that a string over C. And likewise, using the set D, the alphabet D, we could generate this string, cats and dogs, and that's a string over a D. We sometimes call this, in English, we call this a sentence. Okay. So, elephants is a legal string on this alphabet, let's say, because it's an understandable word. Cats and dogs is a legal string on this alphabet because it's a valid sentence, right? So that brings us to the idea of a language. So a language is a set of legal strings over some alphabet A. Legal strings. Here's some example legal strings. So on the on set A, we could define a language, L0, as being all the words in the Scrabble dictionary. And we'll call that a language over A. So that's not every word that you could, or every string that you could possibly generate here, right? Because many, if you just started generating random strings, many would just be gibberish. And then you'd get an elephant in there every once in a while, right? So here's one way to define what's a valid or legal string. Okay. Another way is you could just list out explicitly what the strings might be, and so using this alphabet, we could generate these strings. And here I've just counted in binary and then dot 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 to indicate a pattern. So I'm sort of saying that any binary number that you could generate using these symbols is valid in this language L1. We call that a language over B. We could also generate a language L2 and say that consists of all strings beginning with 0. So that's a further restriction on what's considered to be valid. All right. Or I could outright list that these are the 4 strings that are acceptable on language for language 3 on alphabet C. All right. So we got alphabets, we got strings, we got languages. Alphabets are atomic symbols. We string those together to make strings, and then of all the possible strings that we could generate, some of those are going to be a language. And by some, I mean the ones that are legal. So what defines legal? Well, a grammar defines legal. So we have this idea of a grammar. Okay, a grammar is the rules that determine legal strings on an alphabet. Just like in English, when you speak, certain things are grammatically correct and certain things are not. Right? So a grammar basically defines what a valid sentence is for English. It also defines what a valid string is on any alphabet, generally speaking. So you can think of a grammar as a function, and it would look like this in function notation. So like L0 I've defined as all the words in this Scrabble dictionary. So there is a grammar G0 that operates on set A that produces this language L0. And L0 is defined as all the words in the Scrabble dictionary. Right? And it uses set A, which is this alphabet here, to generate strings, and then a subset of those strings is the language L0. And there's a grammar G0 that generates that language. Okay, fun stuff. And so forth. You could define L1 as the language. So you could say L1 is what does L1 operate on? Language alphabet B. You could say something like that. L1 is a language given by the grammar G1 operating on alphabet B. Okay. So here's some typical notations, some of which we've seen already, and some of which are new. So we typically use capital letters to indicate alphabets. We use lowercase letters at the beginning of the regular alphabet to indicate symbols in those alphabets. And we have a need to represent strings using one symbol. So we've reserved these letters at the end of the regular alphabet, the regular, English alphabet. We've reserved these symbols to represent strings of a language. We'll talk about that more in a bit. Okay, we've already seen this concatenation operator. We've got a new guy called choice. It's just a bar operator. And we've got the null string, which we've seen before. This is a symbol to indicate a string of 0 length. And then we need a way to represent every possible string that you could generate on an alphabet. So we use the star closure symbol here, because remember, a grammar defines what's legal, right? A grammar defines what's a legal string. So we need a way to represent every possible string. So Basically, a language is a subset of the star closure, right? A language is a subset of the star closure because a language is a set of valid strings on an alphabet. Not all possible strings, but just valid strings. Okay? Fun stuff. Now, before we go on, let's kind of deal with what we've laid out here. So lambda is the null string. So if you wrote lambda x, that's the same as writing x lambda, and it's the same as writing x. Why don't you just write x? Well, sometimes we need a way to represent a substitution that we've done, and that is a way to represent substituting nothing into a string. So lambda is useful for that, and we'll see that in a bit. But I'm just trying to indicate here that lambda is the null string. But it is handy to be able to represent it, and we'll see that in a minute. The star closure, that is the number of strings that you can, the number of strings in the star closure is infinite. That's saying that given an alphabet, it's possible to generate an infinite number of strings in that alphabet. But the length of each string is finite. Okay, the length of each string, and it's possible to be generated on an alphabet. The length is finite. Strictly speaking, the way we define these strings is it's not strictly speaking finite, but as a practical point, they are finite. So that's a little bit confusing, but let me talk about these two lines here. Let me just talk about that in terms of two different alphabets. Let's consider the alphabet A here. So what we're saying is the number of possible strings that you could generate with this alphabet is infinite. But each string that you generate has a finite length. So one of those strings that you could generate is elephant, and that's finite. But there's an infinite number of strings that you could generate. Okay, that's what these two lines mean in the context of this alphabet. Let's consider this alphabet. Now this is an alphabet here because an alphabet is a finite set of atomic symbols, and each of these words is indivisible. That is, each of these words is atomic. Okay, so this line right here is saying that the number of ways that you could string together these words is infinite. So we're saying it's possible to speak an infinite number of sentences in English. Would you all agree with that? I hope so, because it's kind of saying that English is powerful enough to say anything. Things that haven't even been imagined yet could still be spoken of. Right, because the number of sentences that you could generate is infinite. That's what this line here is saying. This cardinality of the star closure is infinite for any set. Here we're talking about set D, where we're generating sentences. But the length of each sentence is going to be finite. That's what this line is saying. The length of each sentence in English is going to be finite. Which is true. I mean, as practically speaking, that's what we do. We also limit the lengths of words. But in theory, they could be infinite. Mathematically speaking, they could be infinite. So this thing here is more, this line here, this statement here is more of a practical thing than an infinite thing. All right, I hope that wasn't too mathy. I mean, sometimes math is just, TMI, right? All right, why are we doing this junk? Well, because so far we've been talking about finite state acceptors, and they're very powerful, right? Finite state machines, finite state acceptors, those are powerful, but they do have limitations. So, for example, now I'm going to use the word pure. There's no pure FSA for the following language. The language consisting of symmetrical strings like this, strings that have the same number of one symbol on one side as on the other. So here I have one A on one side and one B, two A's, two B's, three A's, three B's, symmetrical strings, so semi-symmetrical, I suppose. But there's no way to generate an FSA for that. Also for palindromes, things that are mirrors on either side, like radar, or if your alphabet was just A's and B's, it'd be things like this, ABA, ABA. Like they're mirrors about, they're the same on either side of the middle, okay? There's no way to generate palindromes with a finite state machine or code, right? So we have finite state machines in compilers that check your code for syntactic errors, right? So your code has a palindromic kind of, or a symmetrical kind of structure to it. That is, for every curly bracket, you have a matching closing curly bracket. And for every left paren, you have a right paren, like that, right? And these guys are nested. So if you have 4 of these guys this way, you better have 4 going that way. So it's a kind of symmetry, similar to what I'm talking about up here. And I'm asserting to you that there is no pure FSA that can check for these. And now, why is that? Because there's an infinite number of states here. You could write a program with any number of these, and for a pure FSA, you would need a state to keep track of each one of these. So a finite state machine has finite states. It has a finite number of states, but here the states varies, and it varies. It's not going to be infinite, but it could be any number. So there's no way to generate a pure FSA with that. Now you can put a counter in there and sort of modify an FSA, but that starts to become rather kludgy and messy. Okay, so what we need is something better than an FSA, and we have that. We have formal grammars. Okay, so what I just said was finite state acceptors are pretty powerful, but they have limitations for certain kinds of strings, for detecting strings of a certain format, like shows up in code and in other things. So we have something called a formal grammar, which is a more powerful way to do that. All right, before we move on, another way to understand grammars is to think about what we already know with human natural languages. We're all natural language speakers. Some people think that grammar in humans is partly hardwired, or partly, you could say, instinctive. That is, you're born with the ability to deal with grammars. And twins is a good example. Is twins will develop what they call twin speak, which is their own language. So they make up their own language. And there's other evidence of that. I'm not an expert on that, of course, but there does seem to be some evidence that at least the very basic parts of grammar are sort of hardwired into our brains as humans. Anyway, humans use something called phase-structured grammar. There's a guy, Noam Chomsky, that's still around that, at last time I checked, that worked a lot on this stuff. So here's an example of grammar that we all know, right? If you're an English speaker, any language has a similar grammar. Sometimes they mix up the order of these things in different languages, but they all have similar grammar. So in English, we have a sentence. A sentence can be broken up into a subject and a predicate. Yes? A subject can be something like any number of adjectives. So here's the star closure on adjectives. So 0 or more adjectives, and then a noun. Okay, the predicate can be broken up into a verb and an object. And here's some nouns that I've defined. Cat, dog, boy. So those are terminals. Okay? These things in this corner, in the pointy brackets, are non-terminals. That is, they're substituted for something until you get to a terminal, right? And here's some examples of some verbs in this sort of mini English I'm giving you. Here's an example. So object is broken up into 0 or more adverbs, then we have infinitives in English, and then 0 or more adjectives, and then a noun, right? This was like 10th grade. Well, for me, it was 10th grade. I had a really good English teacher in 10th grade who really, maybe I just thought he was good because he looked at grammars very structured, in a very structured way, kind of like a coder would. And of course, I'm inclined to be a coder. That's why I'm talking about this stuff right now. But anyway, I remember learning all this stuff at this level of formality in my 10th grade English class. Anyway, here's an infinitive. Here's some adjectives: big, fat, white, and red. All right. So given this grammar, you can say an infinite number of sentences. For example, you could say something like, the big fat red cat ran to the white boy, right? So you know this part of this is subject, part of it's predicate, and then the subject breaks up into adjectives, big, fat, red, right, and then noun, cat, like that. Right, so you do repeated substitutions of these things in the pointy brackets until you end up with a terminal, atomic symbol, like boy, cat, dog. Yeah, so that's natural language. So Noam Chomsky, and others use this kind of thing to analyze natural languages, and it turns out that this kind of thing is very useful for us coders, right? So it comes from the study of natural language. All right, what you've all been waiting for. What the heck is a grammar, math speaking? And so we're going to start out with something called context-free grammars, and here we go. What are these things from a mathematical perspective? And then we'll look at examples. Okay. So here's a formal definition of a grammar. We're going to start out with a certain kind of grammar called a context-free grammar. Okay, so a context-free grammar, G, consists of this stuff: a set of terminals, T. Terminals like, up here we were talking about cats and dogs and stuff, but we're going to use single-letter terminals. Okay, then we had a set of non-terminal symbols, N. Then we have a vocabulary, which is the union of these two things. And then we have one of these non-terminals is the start symbol, S. And then we have these productions, P, which look like this. We have, in a context-free grammar, that is, they look like this. Non-terminal on this side yields W, or this might be omega. I have to go check. I'll just say W. So non-terminal on the left-hand side can be replaced by a string W, and W is some combination of terminals and non-terminals. So W is an element of the star closure of V. And V is the union of terminals and non-terminals. So basically, this is saying that W is some combination of terminals and non-terminals. So we take non-terminal symbols on the left-hand side and replace them with a little string W consisting of terminals and non-terminals. Yeah. So here's some conventions. We use lowercase letters at the start of the regular alphabet for terminal symbols. A terminal meaning we're done. We can't replace it anymore. It's terminal. It's the end. And then we use capital letters for non-terminals. We reserve the capital letter S for the start symbol. Yeah. So let's look. We'll look at an example in a bit, but before we do that, if you were going to automate this stuff to create a string acceptor or a string generator, that might look something like this. So you'd start out with a grammar, right? You think back for a bit when we were talking about regular expressions. Those were these patterns of symbols, and those can be crunched into finite state machines. So now what we're talking about is grammars, which are symbolically are going to be all of this stuff here, right? So you define the grammar. It's going to be some more elaborate patterns, you could say. You take those elaborate patterns, which constitute a definition of a grammar, You run that into an algorithm that crunches that and generates a machine called an acceptor. So this is how you would create a syntax checker in a compiler. So you define the grammar, which is basically defining the rules for the language. Like if you were going to write a new language called C++, C triple plus. So you would define that language by writing this grammar. Okay, then you feed that grammar into this algorithm. The algorithm generates an acceptor. Now you could take some source code written in this new C triple plus and run it through the acceptor, and it would tell you if it's syntactically correct. Okay, and then you could go back. Let's say you wanted to add a feature to your new language called C triple plus. You add some feature by redefining the grammar. Okay, then you run that through this automation process to produce a new compiler, which is an acceptor, and then you run your source code through that compiler, right? So most of the time, at the level that we're at, we're dealing with just using compilers, right? We write source code, we run them through these acceptors, and the compiler spits out, is this thing good or not, right? But as you guys move on in your education, you'll get to a point where you're going to be able to define grammars and write your own languages. That's what really computer science is really about. It's not just about using compilers. It's about creating compilers, right? Somebody has to write compilers, and that's what computer scientists do. So there's some courses at the junior level and above where you just write new languages, basically. Okay, so this is thinking about it as an acceptor. A little bit harder is a machine that generates strings, but it's similar. You'd take the same grammar here and you'd run it through an algorithm, and you'd produce a machine that can talk. So this would be a machine that could write code. This is much harder to do in terms of writing code. It's a little easier to do in terms of writing natural language. Right? So what I'm saying here is you could define a grammar for English, run that through an algorithm, and produce a machine that can talk. And we already have that. It's pretty easy to talk. Much harder to listen. Oh well, it's ironic. It's hard. It's very easy to listen to computer code. That is, it's easy to syntactically check computer code, but it's hard to automatically generate computer code. But the converse is true with natural languages. It's pretty easy to write a machine that'll generate natural language. It's much, much harder to write a machine that will accept natural language. Think about that. All right. Backing up for just a second, we have this formal definition of a context-free grammar. We're going to have terminals, non-terminals, and then productions. All right, let's look at that as an example. Or rather, let's look at some examples of that. Here's one. What you've all been waiting for. Examples of context-free grammars. Because that's what the homework asks you to do, is generate these grammars, answer questions about these grammars, that kind of stuff. So here's a grammar G1. These are my terminal symbols. Alpha, I'm sorry, I turned Greek for a second there, or was it Latin? But anyway, A, B, and lambda. Our non-terminals are capital S and capital A, and S is the start symbol. And I have these productions, so I have S can be replaced with little a, big A, right? So S can be replaced with little a, big A. I could also replace S with little a and big S. I could replace big A with B, little b. This is like taking a sentence and breaking it up into like a word and the predicate or something like that. What I'm saying there is it's conceptually vaguely similar to natural languages, but I don't know if it's worth trying to map that exactly at this point. But it's kind of like what you do already when you talk. Okay. Anyway, we have these four productions. We can replace capital S with little a, big A. We could replace capital S with little a, big S. We could replace capital A with little b. We could replace capital A with lambda. So this is a terminal production. That is, once you've done this substitution here, you're done because you have little b as a terminal. And once you've done this substitution, you're done because you have lambda. And these two are non-terminal because you replace s with little a, big A, then big A is a non-terminal, and you could do one of these other two productions to get rid of the big A. So you could say all kinds of things. Well, this particular grammar here happens to be describable in one sentence. That is, you can describe what this grammar does with this sentence. Basically, this grammar will accept strings of all A's with one optional B at the end. Let's look at a couple of production sequences here, and then we'll see if we can explain why this is the case here. But let's ask the question: is the string AB valid? That is the string AB an element of the language generated by G1? So basically, we're just asking: is AB a valid string? And it's valid if there is a sequence of productions that will yield AB, and there are. So AB is a valid string in the language. And the series of productions we can go through in detail. So you start with this one, big S equals little a, big A. Then we do this one, we replace the big A with B. So this big A gets replaced with B, and you end up with little a, little b. So it's valid because there is a sequence of these productions here that will generate this string. Likewise, we're asking the question: is the string AAB valid? That is the string AAB an element of the language produced by G1? And it is, because there's a series of productions that will produce AAB. We start with this guy right here. Then we replace the S with this same production. We replace the S with little a, big A. That's the same production. Then we replace the big A with little b, and we get AAB. Okay? So AAB is valid because there's a series of productions that will produce AAB. So we've sort of demonstrated that these two little strings are valid, but can we demonstrate that this more general description is valid? We can, and that's a little bit more tricky, but the analysis is something like this. So you have to start with S, and if you do either one of these S's, you're just going to get little a's and S's, or big A's. Now, that gives you all little a's. What about the non-terminals S and A? Well, we've already looked at how S's give you little a's and something else. So just doing S over and over again is going to just give you a's, little a's, right? What about the big A? Well, if you do the big A substitution, it gives you a B, but then you're done because B is terminal. Or you could replace the big A with lambda. In either case, you're done. So you see, it's only going to be the little a's, right? Until you stop, and when you stop, you either stop with nothing or you stop with a B. So it's a string of all a's with one optional B at the end. So that's the analysis of this, and the analysis is vary, and sometimes they're very difficult, but this one is manageable. Let's look at another example. So here I have these productions here. What if I just change one of these productions right here? So I'm just going to change this production to this. So here we go. So here's a new grammar. I've just made a change to this one production right here. What happens? Let's look at a couple production chains. So I could generate this string A by doing this production right here, then doing this production to get rid of the capital A, or rather this one. this one to get rid of the capital A. And then the last thing you do is delete the lambdas, because they're just there as placeholders to tell that you've done a particular production, right? Now, just to make it clear that I'm doing this production here, A yields lambda. That's why you write the lambda. That's the only reason for lambda, basically. And then the very last thing you do is get rid of the lambdas. So there's a production. Let's do another one just to kind of play with this guy. We could do this production first, and then we could do this production, and we end up with AB. So here's another production. We could do this production first, get the capital A and the capital S. Then we could do what are we doing here? We're doing this guy. We're doing S yields little a big A. So we're replacing this S here with little a big A. And this generates this W, right? This is a W. It's a combination of terminals and non-terminals. A W, an element of the V star closure. Remember from way back in definitions? All right, continuing with productions. What are we doing here? We're doing this production now, where we're replacing this capital A right here with a little b. Then we're doing this production where we're replacing this big capital A with lambda. And then the last thing you do is get rid of the lambdas, and you end up with a BA. So there's three different productions. One yields A, one yields AB, one yields BA. What can we say in general about this guy? Not much. I mean, we can say that it accepts A, B, and BA, and it also happens to accept BAB and lots of other strings. It's difficult to characterize this particular grammar in a simple definition. Unlike this guy up here, the previous one we did, where it's easy to characterize this grammar G1 in terms of a single line description. The second grammar G2 is much more difficult to characterize. Okay, moving right along. Let's talk about some rules of how you might want to construct a formal grammar, and then we'll look at some characteristics, and then we'll look at some more examples. Okay, so let's say somebody asked you to construct a grammar for all strings on the alphabet AB, which begin with A and end with B. So one way to do it is to view the whole thing. So this production here, S yields little a, big A, B. Once again, S yields little a, big A, little b. This will do the end with A and or begin with A and end with B thing. It'll do it, right? Because you do this production, it begins with A and ends with B. That'll take care of it. Then, well, all we need is to be able to put anything we want in the middle. So this series of productions here for capital A, this will allow you to generate any string. So this line here is really three productions. It's A yields little a, big A, and it's also A yields little b, big A, and A yields lambda. So these choice bars are just a way to represent, in this case, three productions on one line. It's just a compact way to represent three separate productions. Anyway, these productions here you can say anything with these productions, right? You could put in a little a and something else, or you can put in a little b and something else, or you could shut up and put in a lambda and stop talking, right? And that's something else, the big A, you just keep repeating this guy over and over again to put in little a's or little b's, right? So you can say anything you want with this, because you can put in little a's and little b's as many times as you want, and then whenever you're done, you just put in a lambda for A. Okay, so this is kind of a handy way to say anything, this series of productions. And then this first production maintains this beginning and end condition that we want. Okay, so that's one strategy, is view the whole. Another way is this optimal path, kind of like you might generate a finite state acceptor. So here, start off with the little a that you need at the beginning, right? And then terminate with the little b you need at the end. And then modify this saying anything stuff by making sure that you can't terminate in an a. So here I could add more a's and something, or I could add more b's and something, or I could add a b, and a capital B, and then that b allows me to terminate. Do you see? So the only way to terminate strings in this is with this production here. This is the only terminal production, and it yields a b that we want at the end. Okay, so the start symbol generates the a we need at the beginning, and then the big B production generates the little b we need at the end. And then this stuff here allows us to say anything we want, except terminating. Okay, so two different ways to define a grammar that will satisfy this condition. Okay, we'll look at some more examples, but before we do that, let's look at some characteristics of CFGs, because we're going to be generating CFGs, so we need to make sure that we do them correctly. And these are some conditions that need to be satisfied, right? So a context-free grammar must have these three things. 1, 2, 3. It must have choice. So you need to have more than one non-terminal to something production. You have to have choice, because if you don't, then you would be saying the same thing every time. Remember the Matrix? In the Matrix, Neo, they were asking him about choice and free will, and he says, yeah, I like what did he say? I don't like to think that my future is predetermined, or something like that, right? He believed in choice. Otherwise, the future is predetermined, right? So you have to have choice. Otherwise, there's only one thing you could say all the time. So you have to have choice. Okay, you have to have recursion. Otherwise, the language would only be finite, right? If you can't continually plug back in, then you can only say a certain number of sentences, and that's no fun. So there's two kinds of recursion. There's recursions where the non-terminal shows up on both sides. That's direct recursion, right? You got a non-terminal here, replace, and then the same non-terminal on the other side, right? So I could keep applying this A into the A, over and over again. That's direct. And then here's indirect recursion, where I have big A to big B, and then big B to big A, right? So I could do this substitution, get a big B, and then I could do this substitution, get a big A, and then I could do this substitution, get a big B, and this substitution, get a big A, recursively. So there's direct recursion and indirect recursion. You need that to make sure that the language is infinite. Okay, then you need a way to stop talking. Yeah, so you need to have some terminal production. So you need to have something that goes to lambda or goes to some terminal symbol. Otherwise, the strings won't terminate. Okay, so these are three conditions you can check when you're asked to generate a CFG. Run this check to make sure that it's a valid CFG. Make sure that you have choice, make sure that you have recursion, make sure that you have a base case. All right, I think we're ready to actually look at some example grammars now. Oh, no, we're not. There's other kinds of grammars. So far we've been looking at context-free grammars. CFGs, context-free grammars. There's other kinds. You need to understand that there's other kinds so that you can avoid them. All right? Or at least right now, in the state of computer science right now, we tend to avoid these other kinds of grammars. Maybe you'll need that in the future, but so another kind of grammar is something called a context-sensitive grammar. In a context-sensitive grammar, replacing a non-terminal N depends on what is around the non-terminal, the context, right? The things that are around the non-terminal is what we call the context. Like in a human English discussion, there's a context, right? People are saying things with their words, but there's a context to understand those words, right? It's important to keep the context in mind, otherwise you can have a lot of misunderstandings. That's what's going on in the world right now. Sometimes there's a lack of context, in my opinion. Anyway, here's an example, context-sensitive grammar. So here, look, I have a non-terminal here, capital B. That's a non-terminal. But on the left-hand side, we have terminals around the non-terminal. They don't actually, yeah, that's right. So I can do this production, capital B when there are A's around it. Okay? And what I'm still just replacing the non-terminal B with terminals, in this case, little b, big A, right? So the actual substitution is big B. Here, I'll underline it. The actual substitution is big B with little ba. That's the actual substitution, but I can only apply the substitution when there are little a's around the b. That's the context. That is, you can only substitute big B for little ba when big B has two little a's around it. Think about it in terms of an English conversation. You can only say certain things if you can only say certain things when other people are talking about those things. That's the secret to good conversation, is stay on the subject, You can't just say anything you want, right? Okay, so that's a context-sensitive grammar, and we'll look at an example of that. Another kind of grammar is an unrestricted grammar, and this is a more free grammar. In this case, you can replace other things besides the ends. So like on this one, we're only replacing the big B with the little ba. But in here, in an unrestricted grammar, here we're replacing we're replacing the context. So we can apply this production when there's two A's, but we can substitute really the whole freaking thing, right? So we're substituting, let's see. We're substituting the whole thing. This whole thing, pen keeps dying. We're substituting this whole thing for this whole thing. So we can, context is still important, but in this case, we're sort of changing the subject, right? Like here, like A could be apples. People are talking about apples. So you say something about apples and you still bring over the apples. But here people are talking about apples and you just change the subject completely to, you're not even talking about apples anymore. All right? So there's context sensitive, where the substitutions you can apply are dependent on what's around the non-terminal. And then there's unrestricted, where you replace things besides the non-terminals. So here I'm just commenting about some analogies to natural language, which I think I've already spoken about already. Okay, I think we've covered enough theory that we can actually get into some examples of these three things. So first of all, here's a context-free, a context-sensitive, and an unrestricted. All right, context-free, context-sensitive, unrestricted. And then we'll look at just context-free. Context-free is what computer science deals with mostly. Context-free. We just want to learn about the other two just so that we can avoid them. So here's a context-free. So I've got these terminals, A and B, and the non-terminals, S and A. I've got these three productions. Right? I'm using the choice bar to indicate really three separate productions that start with S. And then I've got another three productions that start with capital A. One thing I could say with this grammar is I could say ABA by this series of productions. So start out with this first production here. No, the second one rather. Start off with the second one. I'm just saying this, you know, just starting with S, and then I'm little a, big A. Then I'm applying this production here, the little b, big A. I'm substituting this big A here for little b, big A, and I get that. Then I'm substituting big A for little a, that's here, and I get ABA. So that's a context-free grammar. You're just substituting non-terminals for some combination of terminals and non-terminals. Okay, what about a context-sensitive production? Here's a context-sensitive grammar where there's context around the non-terminals, right? So I can do this production here. I can substitute the big A for one of these two things only when there's a little b next to it. Here I can substitute the big A for one of these two things, but only when there's a little a next to it. So you might yield something like this. You might start off with S and say big A. Then I might apply because I have a little a next to the big A. I can do this. Oh, I'm missing something here. Indeed I am. There should be another A on here. I gotta fix the notes. Because here there's a little a next to the big A. That means I can substitute the big A for two little a's. So basically I'm substituting this big A for these two little a's. That's a context-sensitive grammar. And then I've got a context-free grammar. Just go all the way up here. Got a context-free grammar here. Or rather, an unrestricted grammar. Sorry about that. I got an unrestricted grammar. So on an unrestricted grammar, you're replacing things in addition to the non-terminals. So for example, here I'm replacing big A, little b with big B. So the little b goes away. And here, the little a and the little a and the big B, the little a and the big B go away and get replaced by big B. And you could say these things in here. I'm gonna just leave that to you to look. Well, yeah, okay, we'll do it. I'm just getting a little bit tired here, but anyway, so we have the this guy generates this guy. We're doing the second production up here. Then we've got a big AB, so we've got this big AB thing. We can replace. No. That wouldn't yield this. We must be replacing here this thing. We're doing the whole little a, big A, B thing with big BB. So here we're replacing all of this with all of this. Then we have we're just doing the big B with the little b. Yeah, you could do the second one if you want on your own. Anyway, this is 3 examples of a context-free grammar, a context-sensitive grammar, and a type 0 grammar. All right. Once again, mostly we're gonna deal with context-free. CFG is what we want. Okay, computer science has learned to restrict the field to context-free grammars. It's important to understand that these other 2 exist, but we typically don't use them. So let's spend the rest of this long lecture in just dealing with analyzing some context-free grammars. Okay? So here we go. Here's a context-free grammar. There's some terminals, there's some non-terminals, here's some productions. It's context-free, so we just have single non-terminals on the left-hand side and then combinations of terminals and non-terminals on the right-hand side. We can ask a question like, is this string in the language? And the proof that it's in the language is if there's a series of productions that generates that string. And there is. See, here's that string can be generated here. Now, I'm introducing a format here because it gets kind of hard to see what's getting replaced. So what I've done is I've indicated the left-hand side using bold, and then I've indicated the right-hand side using green. So I don't know if this green is showing up well in the video. I don't think it is, but you might need to look at the printed notes to where the green shows up a little bit better. But I'm starting off with this first production. So S yields little bs. So big S is bold, and then bs is green. Then I'm taking this S, which I've made bold, and I'm replacing it with bs again. So I've made this bs green. I just did the same, this first production I just did it twice. Then I'm doing it again, and I'm replacing, no, I'm doing the whoops, I messed up my papers here. Then I'm doing this second production here. I'm replacing the big S with little a, big A. So I've made the big S bold and the little a and the big A green. Okay, so I suggest you do this on your homework, just not only for me, but just for your own good, to keep this stuff straight. Then I'm doing one of these A productions. Which one? The first one. I'm replacing this big A with little b, big A. So I've made the big A bold, and I made the little b, big A green. And then I do that again. Then I'm doing this one, doing this little AS thingy here. Then I'm doing one of these S's, I think. This is, what am I doing here? BBA, BB, BBA, BBA, S. I'm doing S is B, I think. Yeah, this shouldn't be green. This guy? No green. I gotta go fix that. I'm gonna go fix that in the notes. Anywho, that's one context-free grammar in a series of productions to answer the question, is this a valid string? And it is a valid string. Let's look at some more. What about this stuff? We got some more terminals, A, B, and C this time. We've got some non-terminals. We've got these productions. You know, some different productions. Let's check if we have choice, recursion, and base case. Here we've got choice. Cool. Here's choice again. So we got lots of choice. Do we have recursion? Here we do. Right, I've got big A on this side and big A on that side. Big A and big A and big B and big B. So that's recursion. That's cool. I've got base case. I've got a little b here. That's my base case. Looks like these are all going to end in little b, right? Because the only terminals are little a, little b, and b. So it looks like all these strings will end in b. Anyway, we can ask, is this string an element of the language generated by this grammar? That is this a valid string? And this series of productions will yield this. Let me see if I can go through this real quick, just to double check if nothing else. So I've got, I start off with the ABA thing. So bold to green, then I'm doing bold A to these green ABs, then I'm doing bold B to the big BA, and then I'm doing the big A to this little AA green. Then I'm doing this big A here to AB here. Then I'm doing this big B to little b here. Then I'm doing this big B to another little b, and I'm doing this big A to AB, then I'm doing this big A to AB. So yeah, fun. One more time. Okay, so let's flip it around and try and generate some context-free grammar. So some guy on the street asks you to find a CFG that accepts all strings over A, B that start with A. So got my start symbol here. This is wrong. Yep, another typo. And this right here is going to break this rule. I could start with S and then immediately introduce a little b. So that breaks this starting with A. Let me just cross this out. Yeah, I'm just going to cross that out. That ought to, this is not going to do any good, just replacing S with S. So I'll get rid of the whole production. Is that going to do it? So this guarantees that I'm going to start with little a. So I could say nothing, or I could say something that starts with A. And then here, this lets me say anything I want, because I could terminate immediately, or I can introduce little a's or little b's and provide the possibility for more substitutions with my big A, or I could stop talking. So I think that'll work if I just get rid of this production. What about, you continue strolling down the street and you run into another person and they go, hi, can you make a CFG that generates all strings over the alphabet AB that do not end in AB? And you say, sure. And you come up with this. And I'm leaving the justification to you. But this will, I'm asserting to you that these series of productions will never end in little AB. And I'm going to leave that to you to understand this. But notice there's some patterns in here. There's there's A generating a little A, and then a little B. Notice I have B's in a column and A's in a column. So there is a justification here, and I did check this a little bit earlier, and I'm pretty sure that it's correct. I just haven't gone through that right now, but I'll leave that to you. All right, what about something that'll accept palindromes? Remember, earlier in this discussion, we were talking about how finite state machines can't accept palindromes without some kind of clues, without like a counter or something, because they have finite states, right? A finite state machine, by definition, has a finite number of states, and palindromes are, they're theoretically infinite. In reality, we're going to stop before we get to infinity, but the number of states varies if you're using a finite state machine. So we can't use a finite state machine, but we can do this. And this guy will generate palindromes, right? Because you do this substitution here, you're guaranteeing the same thing on either side, and then likewise, this is guaranteeing the same thing on either side. So every time you do an S substitution, you're building up a palindrome, because you're adding the same thing to each side, and then you could terminate by just putting a single letter in the middle or nothing, right? So this will very, very easily generate palindromes. That's it. Okay, I hope you enjoyed this stuff. Context-free grammars is mostly what we're concerned with. This stuff is a little bit tricky, and people sometimes find it hard to generate these things, but got to start somewhere. And the value in this, once again, is we want to be able to define grammars so that we can use those to both check languages and generate language. Right? Typically, we build machines that check for syntax in formal computer languages. Syntax checkers are finite or use formal grammars. And if we want to speak in a simulated natural language like English, we can use a grammar to define the kinds of sentences that this machine would say to you. All right, hope this was useful to you. What we're going to do next is we're going to, I have a lab that will generate natural language using a grammar, and it's pretty fun. All right, hope this was useful to you. See you next time. Thanks for listening. Bye-bye.